I am going to discuss a breadth first search in this video. Breadth first search is an algorithm used to traverse or search tree or graph data structures. It starts at the root node or any arbitrary node in a graph and explores all of the neighbor node, all of the adjacent nodes at the current level prior to moving on to the nodes at the next depth level. So, this process continues until all the nodes have been visited, and BFS is typically implemented using a queue data structure. So, it uses queue data structure to implement, and BFS is also called a level order traversal. Generally in BFS, like we would be visiting and exploring all the adjacent vertices. Let us discuss one example. So, here the one tree example is given here, and let us discuss how the breadth first search can be applied on this tree. As I discussed before, the breadth first search uses the queue data structure. You all would have known about the queue data structure. This is how the queue data structure would look like, and we call this queue data structure as first in first out data structure, which means the element which came first would be removed first, would leave the queue first. It's same, like it's similar to our in a real time, like in real life we used to stand in a queue and get the ticket, some like for some other purposes, right? The same concept is only applicable here even in the queue data structure. The one who come first would leave the queue first. Same way here, the element which came first to the queue would be leaving the queue. So, here there are two ends as in real life queue, like we have two ends, right? The one end, like at the one end the people would be leaving the queue, at one end the people would be entering into the queue. Same way here also there are two ends, one is front end and another one is rear end. So, rear end is the place where the new element can be added, entered into the queue, and from the through the front end only the elements can be removed. So, there are two ends, rear and front. So, two different ends are there to perform insertion as well as the deletion. So, this is how the queue data structure is, and this is how the queue data structure would function. So, here even in breadth first search also we are going to implement this, we are going to use the queue data structure only. Create a queue data structure and start visiting the vertex one by one with the help of BFS technique. And here, as I discussed before, it starts usually at the root node or any arbitrary node. So, here in the tree the root node is already given. So, we are going to start from the root node first. The root node is 1. So, we are visiting the root node first. So, once visited, we are supposed to maintain the order in which the vertex are visited here. So, since the vertex is visited here, the vertex 1 is the root node 1 is visited here, I am going to register the vertex 1 over here. Once the node visited, we are supposed to insert the visited node inside the queue as well. Okay, the node 1 is visited. So, which node we are going to visit next? That can be decided, that should be selected, like which node can be explored from the queue only. Like if you check the queue, inside the queue, like at the front end, because only through the front end the elements can be removed. So, which node should be explored, we have to look at the queue and decide. So, if I check the queue, there is only one at the front end, which means I am supposed to explore one. If I explore one, there are two possible vertices are there, 2 and 3. So, if you explore one, we would move to, we can visit the vertex 2 as well as the vertex 3 also can be visited. Once visited, we are supposed to delete the node 1 because the 1 is already explored. So, the 1 can be removed from the queue, and 2 and 3, the newly visited vertices can be included into the queue. So, we are inserting through the rear end and deleting through the front end. So, once if the node is explored, we are supposed to dequeue it from the queue, we are supposed to delete it from the queue. So, the node 1 is visited, I am deleting it from the queue. Now, which node we are supposed to explore next? Look at the queue, look at the front end. If you look at the queue front end, there is 2, which means we are supposed to explore 2 first. If we explore 2, again there are 2 vertices are there, 4 and 5. So, 4 and 5 are visited. Parallelly, we are supposed to maintain here as well, right, under the vertex visited. 1, 2, 3 are already visited. Now, 4 and 5 is also visited. So, once visited, we are supposed to insert it into the queue, and also we are supposed to pop out, like the node 2 is explored, right. So, the explore node we are supposed to remove it from the queue as well. So 2 was explored, so I have removed 2 from the queue, and 4 and 5 was newly visited. So 4 and 5 vertices are newly inserted into the queue. Next, which node should be explored? Look at the queue front end, 3 is there, which means we are supposed to explore 3 next. If I explore 3, I would be visiting the vertex 6 and 7, right. So 6 and 7 would be visited. So once the new nodes are visited, we are supposed to include inside the queue, and also which node was explored now. The node 3 was explored, so delete it from the queue. Next, if you look at the queue front end, there is 4 again, which means we are supposed to explore 4, right. So I am going to explore 4. So once explored, we are supposed to remove it from the queue. So I am exploring 4. Since I explored, I am removing it from the queue. After exploring, I am getting the node 8, which means I have visited the node 8. I am inserting the node 8 into the queue. And if I explore only 8 is the possible vertex I am getting for 4. So the 4 is explored, the 8 is visited, I have included into the queue. The next node to be explored is, look at the front end, that is 5. 5 node should be explored. So I am exploring 5. Yes, I explored 5, but there are no vertex found under the vertex 5. So there are new node visited, no new node available, so we cannot visit any vertex under the node 5. The next node to be visited is, look at the front end, the queue front end, that is 6. So explore 6 now. So cancel 6, and if I explore 6, I would be getting the node 9. So insert into the queue, as well as under the vertex visited, you include the node 9. And the next node to be visited is 7. So try to be explored is 7. So try to explore 7. If I explore 7, there are no possible vertex for 7. So it is explored, but no possible vertices. So new vertices cannot be included into the queue. And the next vertex to be explored is 8. So if I explore 8, there are no vertex found under the vertex 8, so no vertex found, but then still the node 8 the vertex 8 is explored. The next node to be explored is 9. So if I explore 9, I would be getting the node 10, which means I would be newly visiting the vertex 10. So I am inserting the vertex 10, and since the node vertex 9 is explored, I am going to delete it from the queue. Next node to be explored is, if you check the queue front end, both front and rear would be pointing 10 only. Now why? Because in the queue there is only 10, so both front and rear would be pointing only 10. So if I look at the front end, there is only 10, which means I am supposed to explore node 10 next. So if I explore, there is no new vertex found under the node 10. So 10 also, since I explored, there is no new vertex found, but still the 10 is explored, so I am removing it from the queue. So the next new node to be explored is nil, because the queue is empty, there are new vertex found, and there are no new unvisited, like unexplored vertexes found inside the queue. So when the queue is empty, we can stop the process. Now if you check, all the vertices are visited, all the vertices are visited and explored, all the adjacent vertices are, and this is how the BFS concept would work. When it comes to the time complexity for a breadth first search, so this is the order in which the vertices are visited. Let's discuss the time complexity analysis now. So the worst case time complexity of BFS is big O of V plus E, where V is the number of vertices and E is the number of edges in the graph. So visiting each vertex takes constant time, considering each edge also takes constant time here, and this is the time complexity of BFS, big O of V plus E. When it comes to applications where the BFS can be applied, let's discuss few applications. One is shortest path problems. So BFS can be used to find the shortest path in an unweighted graph or a tree. Second application is web crawling. BFS is used by search engines to index web pages by exploring web pages and their links in a breadth-first manner. And third example is puzzle solving. So this BFS can be employed to solve puzzles like the sliding puzzle or the Rubik's cube by exploring possible moves in a breadth-first manner. So these are the sample applications. So this is how the breadth-first search would work. So here it would be visiting, this algorithm would be visiting and exploring all the adjacent vertices at each level, and then only it can move on to the next level. Thank you.